All right, so we've covered that. We've covered the different types of communications and what a broadcast packet looks like. These are the things that they're going to want you guys to be able to calculate. All right, so we discussed the types of IPv4 addresses, and they gave you the RFC 1918 public addresses are globally routed between internet service providers. So we know that Southern is a owner of a full Class B address here. So we actually have a full public Class B. Typically ISPs, AT&T, C-Spire, folks of that nature are going to have these large blocks of public. Everybody in the real world on their lands is using private addresses. These are common blocks of addresses used by organizations to assign IP addresses, and this is because of the depletion. They're already out. So we know anything that starts with a 10 is going to be private. Anything that starts 192.168 is going to be private. Anything that's 172.16, 172.17, 172.18, all the way through 31. So 172.31 would be the end of the private range on a Class B. So all these are usable by us. Which one you use is your choice, because we're the administrators. We'll be able to put whatever we want. But we know we can't let these things directly out on the internet. We have to use something called NAT if we want this to be allowed to the internet, if we want our machines to be allowed out. So you can see NAT is typically enabled on the edge router, connecting us to the internet, talking to the ISP so we can translate those numbers. We talked about some special numbers. 127 is a special number called a loopback. All right, so anytime you guys see a 127, we're using it for testing. This is confusing for folks for some reason. When we ping 127, which we can actually use for testing connectivity to applications as well, but a lot of times you'll see people ping this address. What they're testing is IPv4 bound to the device's adapter, and we're testing it local. So when I hit 127.0.0.1, I'm looking for my computer to respond, or the device that I'm on to respond, to let me know that I have IPv4 enabled and functional. Does it mean the computer's going to get on the internet? No. Does it mean everything's configured right? It does not. It just tells me that I have IPv4 installed and bound to the device's network card. The link local address that you guys see here, inside of Windows and other devices, there's something called a PIPA. So APIPA, a PIPA, automatic private IP addressing. Anytime you guys see this, this is not good. This means that our adapter did not get a dynamically assigned address. Right? So in its in the writing, we've written in so that these machines will auto-calculate an APIPA address, so hopefully some communication can still occur on the LAN. All right, so this is your machine making an attempt to generate its own address that we can use for temporary to do local communications. All right. Anytime I see a 169, I know right out the gate that somebody's got dynamic address configuration turned on their computer, and it's not getting a valid address on the network, because we don't assign those to devices. So like I know everything in here should probably be getting a 10 address of some nature. So if you guys were to pull up and do an IP config, it's going to show you what your address is. Right? So you can see all the different adapters, but you do IP config, and then we should get our adapter that gives us the internet. So that I know is a valid address. So now you guys know if you see a 169.254, the problem is for some reason the device that you're working with is not getting a connection to the network because it's not receiving an address from DHCP server. I think this kind of puts us where we were. You guys can see that there are allocated IPv4 addresses in classes. So RFC 790 in 1981 allocated IPv4 addresses. So from 0 through 127 defines a class A. So the only number that's important here is the first octet. The octets go from left to right when you're looking at them. Okay, so the first octet is going to have that 0, and the ending part is 127. On the class B, it goes from 128 to 191. From 128 to 191. On the class C, it's 192 to 223. We know 223 is some of those public, but I think that they also use some of that in multicast. I know in the 224 for sure, that's the IPv4 multicast. So when we get into class D and E, you won't see these on your LAN unless you're working for some kind of research or governmental entity. Those aren't used in the public-private sector, so you won't see those. So if you see something that's D or E, it's because you're working for a different organization. As you see down at the bottom, classful address allocation was replaced with classless addressing, which ignores the rules of the A, B, and C. Classful addresses wasted many of the IP addresses. Everybody good with class A, B, C? They showed you a pie chart with percentages, the total number of hosts. We know that we can get that 16 million number on the class A that's over here on this right side of the slide by doing some math. We know 2 to the 24 is going to give us that number, or should. When we look at the class B, the 65,534, we know that that's 2 to the 16. I'm getting those numbers because I know that a class A has 24 bits that we can use for host space. A class B has 16 bits we can use for host space. And by default, a class C has 8. So 2 to the 8 would give us the 254 number. Remember, these guys are actually taking off the 2 in the space here for the broadcast and the network address, the loss. All right, so the assignment of the IP addresses, Internet Assigned Numbers Authority, IANA, manages and allocates blocks of IPv4 and IPv6 addresses to 5 regional internet registries. So when we talk, I don't know if I mentioned it in here, but an address has a unique number that's assigned by an association, all right? So IANA is handing these out to these regions. So you can see that there's a AFRINIC, Asian Pacific or APNIC, RIPE, which is your European. You got Latin American, the LAC, NIC, and then we have ARIN out over here in the US, right? Or the North American continent, I guess is more than just the US, right? Everybody can kind of see the map. Now, we can use this for geographic blocking and allowment. So I can allow only US traffic to make a connection. The downfall is that we can buy stuff in other countries if we were standing at boxes. So if I put something somewhere else, they're not going to be able to block me if I'm using a box over in Europe to get places if they're blocking against the US. So RIRs are responsible for allocating IP addresses to the ISPs, who then provide these addresses to blocks to smaller ISPs and organizations. So we're going to talk about segmentation. So this is where it starts getting interesting. We're going to break things up. So because IPv4 has broadcast traffic, and we know broadcast goes to everybody on the network. So when I send a packet that's broadcast, everybody sees it. So when you guys are doing Wireshark, you guys get to see broadcast. All right, that's how we were able to do the ARP research. So many protocols use this. We know DHCP is one of those. There is some DNS that's broadcast. We know IPv6 eliminates this. We don't have to broadcast an IPv6, right? That's going to be one of the differences. So ARP, DHCP, DNS, there are others out there, but those are some of the well-known protocols that we use day to day all the time. So they point those out that they're broadcasting, they're going everywhere. Because switches propagate broadcast out all interfaces except the interface on which it was received, everybody's going to see it. The only device that stops broadcast is a router. Right? So this is semi-true. So the only device that stops broadcast is a router. There are multi-layer switches that have been added, which are in some form a router, so we can prevent it at the switch in some cases. But routers do not propagate broadcast because broadcast is strictly prohibited to the LAN or the network that it lies on. Right? So that's why the routers stop it. Because every interface on a router is a different network. And so for the broadcast to flow through the router doesn't make sense. Because we're just trying to talk to the things on our network when we broadcast. Each router interface connects to a broadcast domain, and broadcasts are only propagated within that specific broadcast domain. All right. So on this slide right here, you can see this gigabit 0, and they have this yellow square here. So they've encompassed all of the switches because this is one broadcast domain. As the network grows, as the number of switches grows, the number of ports grows, the number of devices, the size of the broadcast domain grows. Right, so we're talking about adding switches, growing the yellow section here on the slide. We grow the broadcast. When we grow broadcast, we're growing the traffic, right? So you guys see 98 first thing in the morning, right? A lot of broadcast, right? Slow to get up and down. If you go down 98 at 12 o'clock in the morning, most days, probably wide open, like no broadcast, clean. All right, same thing with our networks. The more broadcast, the dirtier the network, the slower things get because this creates congestion. So how do we alleviate that problem? We use something called segmentation. All right, so the problem with large broadcast domain is that these hosts generate excessive traffic which negatively affects our network. So what are we going to do? We're going to reduce the size of these broadcast domains. So we shrink things. So one way we can do this is by taking and breaking our networks up. So you can see in this example, they take the 172.16 and they add a 172.16.0 and a 172.16.1. They broke the network into two networks. Took the 400 users from the top slide here, and they've just added a second interface on a router. So now we have two different networks with 200 addresses instead of 4. So you basically split this in two. So the broadcast can't leave LAN 2 to get to LAN 1 and vice versa now. We can still set it up so that the users in LAN 1 can get the stuff on LAN 2 and vice versa, but it won't be broadcast traffic. All right, so that's one way that we can do this. So we know that broadcast is a problem or a potential problem, and the way to fix it is to segment, all right, to shrink the size of our broadcast domains. And one way to do this is by adding switches on 2 different interfaces on a router or 3 different interfaces on a router. Y'all see that down here? The more interfaces you add to the router, the more cost we add to the router. but the smaller the networks get. All right, subnetting reduces the overall network traffic, improves network performance. It can be used to implement security policies between networks or subnets. So anytime that they say subnets, just so you guys know, they're just referring to a different network. So a subnet is just a smaller network. It's just another word for network. Subnetting reduces the number of devices affected by abnormal broadcast traffic. They're used for a variety of reasons, including location, group or function, device type. So you can see here they got different floors with different LANs or networks on them on the building slide over here. They're all connected to different interfaces on the router. The middle one here is by function. So you got admin, human resources, students, accounting. Again, different interfaces. And then device type. All right. They got servers, hosts, printers, all on different LANs. All right, so networks are most easily subnetted at the octet boundaries, the /8, 16, and 24. Notice that using longer prefix lengths decreases the number of hosts per subnet. So we know by default a /24, which is a 255, 255, 255, mask. 255, 255, 255, mask is a class C, and it only has 254 hosts on that network. Whereas a class B that's using a /16, which we know by default is a 255, 255, 00 subnet mask, has 65,000 addresses and devices, or the potential for 65,000. Big difference. It's a lot bigger broadcast domain on a class B than on a class C. All right, so here's the first table. They got a 10.0.0/8. It's subnetted using a /16, and then the second table is /24. So over here on the left, you can see if they do a /16, we've taken a class A that has 16 million addresses, and we've turned it into a bunch of class A's that look like class B's, and now each class A has 65,000 addresses, right? So 10.0 to 10.0.255.254 becomes a network at the top. We're looking at this left chart, going top down. See all the /16s? So they changed from a 255.000 mask, because this is a class A, to a 255.255.00 mask. Remember that /16 just defines how many ones are turned on in the subnet mask from left to right? And by doing this, they've created 256 networks from 0, 1, 2 all the way to 255. So instead of it being 10.0.0.0 and that being the network, we now have 10.0 is a network, 10.1 is a network, 10.2 is a network. Because they've slid where the network starts and stops and where the host devices are. Over here on the right, this other slide, they've taken these class A's and slid it to a /24. So from a /8, which is the default, to a /24, now they've created a whole lot more networks. Because we've borrowed 16 bits. But by borrowing 16 bits, because originally this was a /8, right? That's /24, which means we went from 8 to 24. So 8 minus 24 gives me 16. So I know they borrowed 16 bits. And by doing so, 2 to the 16, we know the math is the 65,536. That's the number of networks that they created. They've taken a class A network and turned it into 65,536 other networks that look like Class Cs. And on each one of these networks, we're going to have 254 addresses. So you can see 10.0.0.0, where the first 3 octets belong to the network now, is a network. It goes from 10.0.0.1 through 254. I'm looking at the top line on the second chart to the right, with 255 being a broadcast. And then it flips down, and now we got a new network, 10.0.1.0. Whereas if we were just doing a Class A, that would all be a part. That would actually be a host address on the Class A network, the 10.0.1.0 would. But because we borrowed and moved the network bits, we've changed the game a little bit here. So this process is called subnetting. So they're showing you from a /24 Class C, if we slide, you can see where you had ends for the network bits on a Class C. If we slide 1 bit, see the N on the top, it moved over. They flipped a 1 on in the subnet mask, which makes it a part of the network. By taking 1 bit, we've created 2 networks, because we know that 1 can be either a 0 or a 1, right? In the 128 field, the real value of this spot doesn't change. And so on each network, when you do this, the space for hosts decreases. So we know by default, if we didn't take that N, if we didn't go to a /25, you'd have 8 bits. 2 to the 8 is 254. We'd have 254 hosts. By borrowing 1, I created 2 networks. I have a 0 network and a 128 network. And on there, we can only have 126 hosts each. That's because your remaining 7 bits are the zeros right there. See the top line? You go down 1 line, they do a /26. They borrow 2 bits. I know 2 to the 2 is 4. It means I can have 4 networks. That's where they're getting the number 4 for the subnets. I would have a 0, a 64, a 128, and a 192. Because that's the value of these bits right here. When I change these, see the 2 that they borrowed in that 4th octet, the farthest one on the right? When you change those, they can either be 0, they can be 64, they can be 128, or if they're both on, they can be 192. You guys see that? Over here in the slide, second one down. So you drop 1 more down, you go to /27. Now I'm borrowing 3 bits. You can see the 3 dark ones there. They change from H to N. So 2 to the 3 gives me 8. So now I have 8 networks. I know I moved over to the 32-bit, so my networks are going to be 0, 32, 64, 96. If you haven't figured it out, where you move the bit to is where the networks are going to start, and they're going to increase by that number. So on the third one down, you borrowed to the 32-bit position, or the 32, right? So the network's going to go by 32. If I borrow to the 16, they're going to go up by 16s. If I borrow to the 8, they're going to go up by 8s. All right. So let's demonstrate subnets. All right. So I was using this for something called wildcard mask that we're going to get into with firewalls. But you guys can take a Excel spreadsheet and you can create different colors so you can track what's going on. And this allows me to create values out here so I can see what's going on. So we're just going to start with a class C. So we know that that's the default mask on a class C. And I'm going to change all these things to the same color. Well, I'm going to change these to the same color. Those can stay that way. Let me get rid of all this stuff out here that makes no sense. All right, so I'm going to do a 0 for the first or the third octet here. So everywhere we have this dark green, is the network bits. Everywhere I got a blank right there, that's going to be our period, because we're going to jump octets. All right, so the third octet is a 0. We know by default that a 192.168 is a class C. We know that a class C has a /24 by default. So it's all one network. So everything that starts 192.168, 0, which the 0 is coming from over here on this build, is always going to have these zeros. Because if this is our subnet mask over here, the 255, this third octet is right here, right, D through K. If any of these bits change, I'm affecting the network. So if we're talking about an interface on a router and I'm addressing stuff on that interface, and this is the third octet, if any of this changes, so that becomes a 1, the corresponding value is 8, right? Everybody buy that? 0 and 8 are two different numbers. That means that this is a different network. Okay? So when you're looking at things and you're assigning things on a network, we need to stay on that network unless we're intentionally moving over to a different network to address different machines. Does that make sense? So this number right here that we're going to learn that we can change defines these network bits. So in the previous slide, in the PowerPoint, we saw them take and change this to a .128. So they moved this from a /24 to a /25. So what they're doing is they're taking this right here all the way down, and we're saying, okay, this doesn't belong to host anymore. They're changing the color, and they're borrowing. So this is now part of the network because they borrowed an extra bit. So if you guys were making this 0, the network number would be, oh, not 10, 192.168.0.0/25. So anytime we have all zeros, so this lighter green would be what we call the host field. I didn't go far enough over. So the lighter green would be what we call the host field. And so anytime you have all zeros in the host field, you're defining the network address, which is what I just gave you right here. Anytime you guys put all ones in the host field, you guys are defining the broadcast address for that network. So what's my broadcast address that I just created for this network above me? So I get this third 0 from over here, because all these things right here are 0. So what's this add up to? Y'all help me out. I know the answer. What are all those ones? When we turn those ones on, what do they add up to? Hmm? 127. I agree with that. So I don't know if you noticed, but when you have all ones, it's one less than the number in front of it. So 128 bit is right here, and it's off. So one less than 128 is everything up in front of it on, which would be 127. So that would be the broadcast for this network. The host numbers that they're getting is anything in between. So if I have any of these bits on, if it's not all zeros and it's not all ones, it's an IP address on the network. It's not all zeros and it's not all ones in the host field. Then we actually have an IP address. So you can tell the network that it falls on because we have network bits. That's the purpose of the subnet mask. So anything in between here, in the 0 and the 127, so if you were wanting to write the range, it'd be that. Which if we add that up, that's 3. That's in between 1 and 126. That's 1. That's in between. I do 1s across the board. We know that's 1 less than 64. That's 63. That's in between. Y'all agree with that? If I change, so this bit was the one we borrowed. Over here, because we have a 255, this is not allowed to change. It has to stay. But because we have a 128 and we borrowed this, the only thing we've used in the network is the zeros. So watch this. Boom, 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 boom. We're now on a different network, and all of our addresses just changed because the 128's on. So we said all zeros in the host field gives us our network, right? So it wouldn't be 192.168.0 anymore. It'd be 128. 0.128. That's the network. All ones, we have the 128 bit on, so the broadcast just changed. It's now 255. This can't be accurate anymore because I'm not on that same network. It's got to be in between the 128 and the 255. So my guess is that it's going to fall into there. So I take 3 and add it to 128, it's 131. That's in between there. If I add 1 to 128, I get 129. That's in between there. If I add 63 to 128, I'm going to get 191. That's in between there. Did y'all see that? So by borrowing 1 bit, you get 2 to the 1 networks. 2 to the 1 is 2, right? So everybody's in agreement that you all just saw 2 networks, a 192.168.0.0 and a 192.168.0.128, because I borrowed a bit. So if I take and I borrow 2 bits, I move my network number. Now my network is going to increase by 2 to the 2. So instead of having 2 networks, I have 4, because those 2 bits now belong to the network. So 1, 0, again, you can't change. If you're working with a specific network, I can't change any of those bits. They have to be the same. Because if I change any of these bits here that belong to the network, I'm jumping networks. So you're either going to have this all zeros, or we're going to have it zeros and ones, or we're going to have it all ones, or we're going to have ones and zeros. But it's going to be one of those 4 combinations. Y'all see that? 2 to the 2 gave us 4, and y'all just saw that I can flip that. If I move those 2 bit positions, I have 4 potential numbers. That's where the 4 networks come from, because those are network bits when I borrow them. This /25 would change. It would become 26 because I borrowed 2 plus 24. This subnet mask out here would have to change. Where are they getting that subnet mask? Right here. So remember the subnet mask, if we're going to turn this into, if we were looking at this as the mask, these have to be 1s anywhere you're going to make network bits. So anytime I change the settings, I'm turning these to 1s and I'm turning everything else to 0s. Remember where we have the host bits? Those are 0 in the subnet mask. So if we add up 1, 1, where you have the 128.64 position, you get 192. You see that? All right, so now I can change any of these bits and I get different networks. So let's start with the first one. So we said all 1s plus our network number gives us the what? All 1s in the host field added to the network number gives us it's not an IP address. I actually had it written on here twice. I heard somebody say it. Broadcast. Tess said broadcast. He's just real quiet. Can't hear. All right, so take this and we add those 1s up. We get what? So the number in front of it would be 64. So all 1s in front of it would be 63. All right. So this number, we know that this is all 0s across this way. So we're going to be in this 192, 168. This is going to become a 63. So our range is definitely wrong. So this is a question mark right now. Our network is a 0, and we get that because if we put all 0s in the host field and we add it to the network bits to the left, we get 192.168.0.0. Y'all agree with that, right? So my guess is that this range is going to be everything in between. So this question needs to be a 1 through 62. There's got to be 1 less than the broadcast and 1 more than the network. Y'all see it? So as long as I don't have all 1s and I don't have all 0s, I have an IP address. So 3 falls in there, 1 falls in there. If I took and flipped all these on, that'd be 1 less than 32. That'd be 31. It falls in between 1 and 62. Y'all agree with that, right? Now, these are your network bits. So if I change this 1 bit, I've just changed the whole network. Oh, I didn't mean to do that. Sorry. So the value of that 64. These belong to the network. So this number right here, we're only playing with this 4th octet. It's going to become a 64. If we add all 1s, which we know is 63, so 63 to 64, we should get what? So this is where you're at, right? 1 less than that. 127. We know all ones in the host field added to the network gives us the broadcast. So our range has to change because 1 through 62 is definitely not above 64 and it's not below 127, right? So my guess is this has got to go from 65 to 126. When we step above the broadcast, we're going to go to the next network would be my guess. So above 127 would be 128. To create 128, we have to change this bit. We know that belongs to the network, right? So we're jumping networks. So the Class C is not too much trouble to do this. We'll figure this out, and then we should be able to move backwards. The only difference is we're adding another octet that we can play with. We have more bits we can borrow. Because with the Class B, we have 16 host bits, all right? And where you're allowed to borrow is the host bits. Y'all didn't see that. So in Class C, that fourth octet, by default in the Class C, belongs to the hosts. We're not allowed to steal from network bits. We steal from host bits. I'm lying to you a little bit because we borrow from network bits too, but that's a whole different story, all right? So you'll tell, IT guys are always lying to you. Oh, we can't do that, right? So we don't want to do that, or maybe we don't need to do it right now. So sometimes we'll change our minds. We'll do things that we say we can't do. Everybody see the bits? So if I borrow another bit, I increase the number of networks. I'm borrowing from the host. We went and borrowed 3. We'd now be 2 to the 3, so we went from 2 networks to 4 networks, and now we'd be going to 8 because we have 3 bits, and I can have 8 combinations, 8 different networks. But as you guys borrow bits, the amount of devices on the network shrink because I have fewer host bits. So you can see when you borrowed 2, we had 6 bits left, whereas originally we have 8. So we go to 2 to the 6 minus 2. So instead of having 254 computers on a network, when we borrow 2 bits, you can see we have 65 to 126 is the number of computers. And if you add that up, it should be 62. On the first network, the 0 network, we had from 1 to 62, right? Because 63 was the broadcast, I believe. And the next number up is the new network. So 64 is this network that we're on now. When we go above 127, we know we're leaving from the broadcast. 128 is going to be the next network. We're going to have from 129 to 190, because 191 is going to be the broadcast, and 192 would be the last network. So 193 to 254 would be those addresses. And so there's 62 hosts on those 4. If we borrow a third bit, we're going to leave 5. So we know 2 to the 5 is 32 minus 2, which means in the next range, if we did this, if we borrowed this 32-bit, we'd now have 8 networks, but on each network, we only have 30 machines. So you got to be careful when we do this, because if we had a network that required 60 machines, we now can't do it because we've borrowed too many bits. So the subnet scheme that you guys choose, like how many bits you borrow or don't borrow, is going to be determined by our real world, right? Like how many devices do we have to have on a network? How many devices are we going to grow to? So today we might have 30. Where are you going to be in 4 years? So hopefully somebody can answer that question. We're planning on growing. Now we've been here for 10 years. We're not changing. We're going to keep it like this. We're happy where we're at. So the answers to those questions define how many bits we borrow and what happens with the network. All right, so I think, and I'll post this in the file section. So you guys can take and manipulate this. You can add, all you got to do is copy, and then you can move over. We can add a whole third set of ones and zeros that you guys can play with. So they built a table for you on slide 45 that shows you a /16. So /16 is a class B, and this is what's going to happen when we start borrowing. We're going to increase the network bits, and by increasing network bits, we know we are basically building more networks. So we get 2 bits, it's 2 to the 2, 4 networks. 3 bits, 2 to the 3, 8 networks. That's the n's. So 2 to the n equals the number of networks. So however many n's that you create. We know the original was /16, it was a class B. So you can see when they get to a /30 down here, the 255, 252, they've added, what, 8 plus 6, 14. So 2 to the 14 networks. But they only left 2 bits. So why did they stop at /30? Why did they leave 2 bits? Is that required? Do you have to have 2 bits? Mr. Starr's nodding his head. So why do we have to have 2 bits? I agree with you.
Network ID, network in the broadcast.
Okay. So if I borrowed everything and left 1 bit, we know we have to have a network and a broadcast. Okay, so can I put any computers on that network? You can have a network and a broadcast, but you wouldn't have anything on it. So you can't do that. You have to leave at least 2. Have to. You guys with me? All right, so N's are network bits, H's are host bits. You got to have at least 2 H's so we can have a network, 2 IP addresses, and a broadcast. So example where we would use something like this is for a point-to-point. So if we have a connection in Hattiesburg and we're connecting it up to Gulfport, I need those 2 ends to talk to one another. There's only 2 things on that network. I just need 2 addresses. So we use a /30. Right? You're never going to have a network with 1 device on it. Doesn't make sense. You're going to be on your own little island. In human nature, sometimes we have folks that do that, right? You don't like being around people, so you want to isolate, hang out by yourself. Call them hermits. And then we get sucked into society. You have to come out of the cave, right? So we can't do that with IPs. We got to have at least 2 things that can talk to one another, otherwise we don't have a network. The more bits you borrow, the fewer number of hosts or devices that you're going to have on the network. I have to borrow bits to create more than 1 network. If I'm just a /16 and I'm a class B, I'm that network. I have 65,000 addresses on my network. I'm 1 network. If I move 1 bit, I now have 32,000 devices on my network, and I'm 2 networks. I move 2 bits, I'm now 4 networks, and I'm going to have 16,000 devices on each network. You'll see how this works? Because it's binary, it goes by 2, so we can divide. So they've got it spelled out for you in a chart. I thought that was kind of nice of them. So y'all can see it. Then they give you an example. It says, create 100 subnets with a /16 prefix. How would you do that? So you want to create 100 subnets. So they're wanting to make 100 networks. Can we do that evenly? So the answer is we're not going to be able to create exactly 100 because we know we go up by 2s, right? We know 2 to the 5 is 32. We know 2 to the 6 is 64. 2 times that's going to be 128. So my guess is that we need to borrow 7 bits, right? Because 128 is bigger than 100, 2 to the 7. So you're going to borrow 7, and then we're going to leave that. Could you borrow one more? Does it still meet the requirement? Yes. So the question, they said create 100 subnets. In this situation, in my mind, okay, well, there's more than one answer to this question. So as long as I borrow at least 7 bits, I've created 100 subnets. Did they define how many hosts that we need? Did they say it in here?
Yeah, keep room for expansion. Right.
So they didn't define, right? So as long as we leave enough, so there's 200, if I borrow 8, I got 256 networks, which is more than 100. And I'm going to have 254 devices on each one of those 256 networks. So as long as that's okay for the size of the networks, could I borrow one more? Sure. I would go to 512 networks, right, by going to 2 to the 9. Better than 100. But now by doing that, I've shrunk my networks down to where I got 126 devices on each network. Every time you borrow a bit, the number of networks increases, but the number of hosts on that network decrease. And they cut in half because we're going by 2s. So 126 or 128 divided by 2 would be 64. We'd be down to 62 per if we went one more beyond. So make sure you leave enough bits for the number of devices that need to go on the network. Change it up. We want 1,000 subnets. Well, you better go to a Class A. Because remember, Class A by default has 16 million hosts. But it leaves us a whole lot of host bits because we have 24 host bits that we can borrow from. I know 2 to the 8. All right, so you can memorize some stuff. 2 to the 8 is 256. Times 2 is 512. All right, so that means I would had to borrow 9. I know I have 24 bits when I'm talking about a Class A. So I'm at 512, not enough to hit 1,000. But if I borrow 10, I'm at 1024. I'm more than 1,000 now. So I borrowed 12 bits from 24 bits. I've left 12 bits. I have 1,000 hosts on every network. I could borrow a 13th bit, 2 to the 13. Now I've got 2,056 networks. But I've shrunk my host space some more. So now instead of 1,000, I only have 500 on each, right?
Right?
Do what?
So it's all in the same broadcast domain. Going back to what we were talking about earlier. How
So
you want to divide that up?
So 10.255.255.255 is broadcast into all the networks, but we would divide them up and each domain would have its own broadcast, or each network. So you see where they're going with this? So these are the kind of things that they're going to throw at you that they want you to be able to answer. Like, okay, here's your Class A. Create me 85 networks. Are you going to be able to create 85 networks? Yes. Are we going to be able to do it exactly at 85? No. Why? Because this is binary. We got multiples of 2. Right? So no, we always are going to double. And when we double in network numbers, we reduce by halves on the host side. It's always going to be like that because we're dealing with binary. We're going to double in size if we borrow, and we're going to shrink in half because of the borrowing.
I don't know. This is probably I have a question. I've always had. I understand our binary is either on or off.
Okay.
Positive charge or no charge.
Okay.
Right? What about a negative charge? That will give you 3 options instead of just 2.
So
that would expand your binary to try again.
Yeah, but you're not talking about addresses and math.
No, I just understand why we have the concept of measuring negative and positive charges.
Okay.
Okay, and no charges neither. There's no signal, right? So if you have the technology to determine a positive, the amplitude of a negative or positive charge, to determine if it's negative or positive, or
So you're talking about changing chips and technology.
right.
Could it possible? Yes. But they don't.
Impossible.
Huh?
Is it impossible to
No, I said it is probably possible, but you're talking about changing everything the way it was started.
right from the 80s and 70s technology?
Correct. So, which they've done because we've got 128-bit processors now, right? Even though we're programming at 64, because it took us forever to get from 16-bit programming to 32-bit programming to 64-bit programming, and now so hardware was always behind us for a long time, and now hardware gets out ahead of us. And so we still change things. We just haven't changed the zeros and one method. It just makes sense. We're just dealing with more of it. All right, so I think that this is a good place to stop. So it gets into the subnet private versus public IPv4 space. I have some worksheets that you guys should now be able to work to determine the network, the broadcast, and the range of host addresses now that you've seen the slide. You guys should be able to identify if something's public or private, because you guys know what the private address ranges are. If it's not private, it's public. Okay?